Good morning, everybody. Hopefully you had a great, excellent weekend. Hopefully you have a great weekend coming up. But today, because of Chemsgiving tomorrow, we got to roll. We got to roll. So let's go over the test. Take a look at page numero uno. A couple people forgot what an off-ball diagram is. Some people give me Bohr models there, other things. Remember, off-ball diagrams are the ups-downs. Off-ball diagrams are the ups-downs. Electric configurations, a couple small things there. It was 1 point, either you got it or you didn't. And then we got right into trends. Things with trends are, they're very easy to flip. So if you flipped one, you might have flipped a bunch. Remember, for ions, metals lose electrons, right? If you lose an electron, then you're going to be smaller. That's why sodium was larger. Nonmetals gain electrons. If you gain electrons, there's going to be more repulsion around the outside. So the ion for a nonmetal is going to be larger. Questions on 1 through 10. For the trend questions, many of you just didn't format it how I told you to format it. So for the trend questions, I said to do 3 things. Number 1, answer it, which you didn't have to answer number 11. Number 2, define the trend. Define the trend. So I need to see somewhere on number 11, electronegativity is a desire for electrons. 3 and 4 were shielding and core charge. You have to talk about shielding and core charge every single time. So electronegativity is a desire for electrons. They're in the same period, so the same shielding. Chlorine has more protons, so more net nuclear pull, and can easier gain an electron. Or you could also say more core charge. Either one of those is okay. It's not about really a full outer shell. This is more about shielding and core charge. So that was 11. 12, what has the higher first ionization energy, barium or calcium? Answer, calcium. Define. Ionization energy is the energy required to remove an electron. 3, same group, same core charge. 4, barium has more shielding, or you could say calcium has less shielding. 5, barium can more easily lose an electron, or it's harder to remove an electron from calcium, depending on how you set it. Questions on the trend questions 11 and 12. No questions. Moving on to math. Math was pretty good. On the first one, this was the sig dig question. So did you have 4 sig digs on 13? Did you have 4 sig digs? 14, you had to do this first, and then sub into wavelength. There is no such thing as a negative wavelength. So there's no such thing as a negative wavelength. So if you had a negative, I took a point off. You cannot have a negative wavelength. You can have a negative energy, but then over here that becomes positive. Questions on 13 or 14? Moving on. 15. Radio, micro, infra, visible, UV, X-ray, cosmic. In which group does this unknown element most likely belong? Well, here's ionization energy 1, 1 electron gone. Ionization energy 2, 2 electrons gone, huge jump. Which means after I lose the second electron, I lost a level of shielding. They're a whole level closer. So it has to be group 2. Jack.
I just put group 2 as a jump from second and third ionization energy is the greatest, most significant, but I lost a point. Is it or something?
Are you sure it wasn't the point for somewhere else on the page?
I'm not sure.
Group 2 is these jump from 2 to 3. Did you get all this other stuff right?
I think so.
Yeah, that's right. I owe you a point. Remind me later. Any other questions on this page? On the last page, first of all, you had to do the electron configuration. So, 1s2, 2s2, 2p6, 3s2, 3p6, 3p2. I'm sorry, 3p6, 4s2, 4s2, which is, that was 1 point. Another point for, that's calcium. And then the last one was where you had to think a little bit. What is the energy required to remove an electron from the valence shell? Well, this is my outermost electron, right? So this was the energy you had to use. So you had to use this number down here. And your lambda is hc over E. So this was your outermost electron. That was the way to figure out on that one.
Probably not overthink that one.
Yeah, there, and it was easy to overthink. But remember, on these charts, the nucleus is here, right? This was your outermost electron, the energy. Does that make sense? Okay. Bonus, this was either 1 or 2. 1 point if you wrote fluorine, and then 1 point if you defined it how you're supposed to do. So you had to define the trend. Nonmetals want to gain electrons. Fluorine has least shielding. Fluorine has the highest core charge. That's why fluorine's the most reactive. But if you wrote fluorine, I gave you 1 point out of 2. And then everybody got 1 point for
I
GIMKIT.
just have a question about like reactivity in general.
Yes.
So as you move down the group, the periodic table, why does the reactivity not increase? Because it's easier to pluck an electron out from a shell that doesn't have greater attraction to the nucleus.
It does. For metals.
So.
But for nonmetals, it doesn't. Because
Okay.
nonmetals want to gain.
Oh.
They're different.
Okay. Good question. All right. Understood.
Okay. Any other questions on the test? Yes.
I'm really confused about my score.
Okay. Let's see.
So that's from the GIMKIT, right?
Yes.
So this was the only page I lost points
So
on.
1, 2,
3, 4, 5, 6, 7. But then this page I didn't lose any, and this I got +2. So
This is wrong. So that should be 55 out of 60 plus 1. It should be 56.
okay.
Write that on there. I'll fix it. Remind me at the end. Bad math. Bad math. Hi, Aubrey. Okay. Okay. So Jack and Brady remind me at the end to give you those points back. Actually, I'll just do it right now. If I don't do it now, I'm not going to forget. Okay, Emily, pass these out, please. Second period. Brady. Jack. Okay. Excellent. Any other questions on the test? AP Classroom. Have you guys all done it?
No.
Due by midnight. Due by midnight.
I know.
Do you guys have your book?
Yes.
You really need it. Go get it. Go get your book.
Are we gonna be taking notes on
Just take a pink pass. What? No, we're gonna do guided notes today. The goal is to get through all of these today. Just risk it for the biscuit. It'd be funny if somebody. Are you the only person that brought your book?
Yeah.
Well done.
We're gonna take notes, and there's probably a possibility we're gonna have to use our book again.
Let it be known on these recorded notes that Jack is the only one who brought his notes, his book. Okay. We're in the 300s. That's kind of crazy.
We're moving.
I mean, if you look at this, how much we've covered.
Yeah. I showed my mom like my binder, and she's like, "Wow, you guys move."
Yeah.
We do.
Like, we're like a little less. We're like, I don't know, 2/5. Like, that looks like exactly 2/5.
Yeah.
Like, pretty good.
It's crazy to think we started way back.
Yeah. We've done it. Great. You did it.
I did the AP Classroom question.
You think you did?
I need to
I've got leftover Romeos for lunch today.
I have leftover canes. Yeah.
Yummy. What if I just started now and we were like half a page in by the time people got back? I'm not like that. Is everyone here 5th period? Nice. No one's missing today.
was that? Chapter 7?
Yeah, now we're doing chapter 8 and 9 together. Chapter 8 and 9. Wow, that's taken a long time.
It just started. That's their fault.
Welcome back.
Thank you.
Oh, yeah, I did.
Welcome back.
Thank you.
I can't wait to go buy a ham tonight after work.
Oh, yes. I cannot wait for tomorrow, guys.
With line paper or.
No, I don't think you will for today. Mr. Knight?
Yeah.
You can invite him. It is his planning. We'll invite him.
That was gonna be a while. I forgot his locker company. Are you serious?
So where is he at now?
At his locker.
Oh, you guys are all the way in Egypt over
Yeah.
there.
He could have just shared.
Siberia.
No, because he presets his locker, but it's jammed, and so he forgot his code. So.
Okay, a couple general announcements before we start these notes. So, we are starting chapters 8 and 9. So we're doing 2 chapters. You okay?
Maybe.
We're doing 2 chapters. Second announcement, remember you're saving all your labs. If for some, remember, so we'll have an actual midterm, like final for this first semester. So we'll have a test, which you guys will all do well on, I promise. Then our final is the lab notebook, which you should all get 100% on, because you just have to turn your labs back in. If for some reason you lost a lab, you have to write a 2-page paper on that lab to replace it. So, just letting you know now.
Why are we not gonna do well in the midterm?
Why?
Huh?
Why are we not gonna do well in the midterm?
I said you will do well.
Oh, I thought you said.
No. Why would I say that? No. I said you will do well on the midterm.
Like, you want to see me cry?
No, you guys will do great. The midterm is going to be the most straightforward review sheet I've given you this year. There you go.
Okay, I was kind of worried. I heard you will
So,
do well, and I was like,
You guys will do well in the midterm. Next announcement, Monday after break, I'm going to the zoo
Yeah, we are.
with Science Club. So I will be recording notes for that day. So this will essentially just be like a study hall that day for you. So you can either watch notes on your own, do something else that period, bring earbuds, however you want to do that. But I will not be here the Monday after break. So you'll be responsible for watching those notes by the Tuesday after break. Cool?
Yeah.
Okay, here we go. Chapter 8, 9. Intramolecular bonding. When you think of intra, what do you think?
Inner.
Inside, right? Has anybody here ever played intramural sports? Yeah. Intramural sports would just be like within Worcester, within Wayne County, right? You don't play other schools in intramural sports, right? Yeah. So this is within. So I like that. And it's bonding between molecules within. Guess what this is based on?
Chemistry.
Nope. This is 2 words, a long one and a short one.
Supercalifragilistic law.
Intermolecular forces.
Oh.
Oh!
Oh, it's cool.
Coulomb's law. All right? Coulomb's law.
It's not going away, is it?
So these are the big bonds that we've talked about. Okay, these are bonds that we've talked about already. So first one is ionic. How does ionic bonding happen? By what? Not sharing, transfer. Ionic bonding is by transfer of electrons. This is mostly chapter 8. Covalent bonding is by sharing of electrons. And then there's a third kind, which is going to kind of blow your mind and kind of say that everything we've learned so far is false. Because that's what chemistry does as we move on. All right? So first, let's review what is electronegativity.
Desire for bonding.
Yes, this is the ability of an atom to attract or desire, whatever, how attract an electron. So, electronegativity is going to be kind of important for these first couple examples. So, an electron cloud diagram. So this is an electron cloud diagram. Can be thought as a probability map of where an electron may be found at one time. In separate atoms, it's simple and could be represented by something like this. So this could be the electron cloud for something like, I don't know, lithium and beryllium, right? Those would be close because those are only like 1 electron away, okay? Why? Well, it's going to be just showing that they're different. I couldn't put in color, so I'm just showing that these are different, okay? When those atoms join together, so let's say this I guess this could also be different. Maybe this could also just be like a nitrogen and a nitrogen, right? N2, a diatomic molecule, any of them. When those join together to form a covalent bond, a pair, put a box around pair, because we are always sharing a pair of electrons is shared. Each atom has its own electronegativity. That's a lot on the small line, which increases, we know, from left to right on the periodic table and from the bottom to the top of a group. What is the most electronegative element? Fluorine. Fluorine. You guys know it's actually FLUO?
Yeah, I know. I see that every time I look at a periodic.
It's actually FLUO. It's fine. It's not important. It's the most electronegative element. If a pair of atoms have basically the same electronegativity, so look at page 306. Look at page 306.
I put too far ahead of now.
Page what?
I'm gonna have to read 2 chapters this far, and that's so messed up.
Yay. Reading is fun.
I like reading, but not.
So do you guys see the chart on the top of page 306? Yes? Yes. Top. That's a whole list of electronegativities. All right, this isn't anything you're going to have to memorize or anything like that. Don't worry. All right? If a pair of atoms have basically the same electronegativity, they will equally share the electrons. The electron cloud will look something like this. Looks something like this. Flip it to page 308. It would look something like that. So, this rarely happens. Because you can see on page 308 and 309, do these look like these are equally sharing? Any of those? The charge. Carbon dioxide is, right?
Yeah. Sulfur tri.
Look at page 309. Carbon dioxide, you could split that in half, yes?
SO3 looks like it's sort of even.
SO3 is, yes?
HCl is not.
None of those other ones are. So there must be something to call those. So here we go. This rarely happens. You only see a true covalent molecule in diatomics. In diatomic molecules or hydrocarbons. Hydrocarbon is like CH4, C2H6, C3H8, and so on and so forth.
What about SO3?
SO3?
Yeah.
I mean, that's not technically a covalent compound. We're going to talk about that in a little bit. These are also non-polar molecules. A non-polar molecule has an even distribution of charge. So you have on these pages, there's 1, 2, 3 polar, right? And 2 that would be considered non-polar. So it doesn't mean you can...
I'm a little confused. So they're like rainbow, right? Like what are the different colors?
We're going to talk about that. That's like the positive and the negative charge. That's all the colors are.
Okay.
So the red is usually the negative, and I think the blue is usually the positive.
So it should be like an equal value.
Yes. If they are evenly distributed, it is a non-polar molecule. Okay? Not even that you can cut it in half, because you would agree there would be no way to cut SO3 in half. Yes? That'd be hard, because you'd be like cutting one of the molecules down the middle. It just has to be an even distribution of charge. Cool?
Yeah.
Okay. Many times, one atom has a much higher electronegativity than the other. So electrons are attracted to more or less. Which one would they be attracted to? The more or less electronegative atom? The more. So circle that. Leading to an electron cloud looking something like this. So the less electronegative is going to be more positive. Agreed? Mm-hmm. The more electronegative is going to be negative because that side is gaining the electrons. Yes? You're with me, yes?
Yeah.
The atom with the higher electronegativity will develop a partial negative charge.
Is there a formula to like determine? Never mind.
There,
What I'm gonna say.
there's no formula for this. This is just based off of electronegativity. And you're not, like, this is super in depth. We're looking more big picture. Okay? Stay with me. Stay with me. The creation of opposite charges at either end of a molecule is called, this is big, a dipole. So put a star by that. It's called a dipole. And now this bond is considered to be polar covalent. Put a star by that as well. Yes. Pretty much all bonds are polar covalent. Hardly anything is truly ionic. Hardly anything is truly covalent. Most of them fall in the middle. Most of them fall in the middle. They're polar covalent. Flip the page. Flip the page. So, you may also hear this called a dipole moment. So maybe it just forms a partial charge for a second. That's still a dipole moment. So let's go back to true covalent bonds. So these are my true covalent bonds. So let's draw a Lewis structure for H2. Hydrogen has how many dots? 1. This hydrogen has how many dots? 1. How do you show sharing electrons? Circle. Would you agree that that would be the Lewis structure for H2?
Yeah.
Yes. So if I was going to draw this, it would look like that. Because we know that each bond is one pair of electrons. Yes?
Yeah.
Diatomic molecule, that is H2. Oxygen has how many valence electrons? 1, 2, 3, 4, 5, 6. This oxygen has 1, 2, 3, 4, 5, 6. It's going to share a pair here, and it's going to share a pair there. Oxygen wants to share 2 pairs of electrons. Agreed?
Yeah.
So this is going to look like, if I was going to draw the Lewis structure, oxygen double bonded to another oxygen, with each one having 2 lone pairs. With each one having 2 lone pairs. You would agree that both of those are, quote, happy, yes? Mm-hmm. This oxygen has 2, 4, 6, 8, and this oxygen has 2, 4, 6, 8. Because each bond requires 2 electrons. See? Try nitrogen on your own. So that's a diatomic molecule. Draw the Lewis dots and then the actual structure. Nitrogen has how many? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Shares 1 pair, shares 2 pairs, shares 3 pairs. So what kind of bond is in between nitrogen? Triple bond. Nitrogen triple bond to a nitrogen. Each one has a lone pair.
Does it matter which electrons you get the circle around?
No, it does not. And then carbon dioxide. Carbon has 1, 2, 3, 4. Oxygen has 1, 2, 3, 4, 5, 6. Another oxygen has 1, 2, 3, 4, 5, 6. It's going to share a pair here. It's going to share a pair here. It's going to share a pair here. And share a pair there.
That is absolutely atrocious.
I know, it's beautiful. It's beautiful. So the Lewis structure for this would look like carbon double bonded to oxygen, double bonded to oxygen, 1, 2, 3, 4, 1, 2, 3, 4. So that's what carbon dioxide would look like.
Can you leave that up?
I can keep that up for a minute. So the difference in electronegativities, this would be a truly covalent compound. This would be a covalent compound. This would be a covalent compound. This is polar covalent. because there's going to be a difference in electronegativities. Look at page 306. Look at page 306 on the bottom. You guys see that little arrow where it's saying covalent to polar covalent? You can see the difference. If it's a difference of 0 for electronegativities, it's actually a covalent compound.
Because it's like N2.
Exactly. You got it. But as there's more of a difference, it becomes more polar. It becomes more polar. Cool? Okay, cool. Covalent bonds occur between atoms with similarities in electronegativity, usually between two nonmetals. The attraction between two atoms makes them increasingly stable, giving lower and lower what? What kind of energies would this give them? What type of energy would it give them the lower energy of? There's only two types of energies. Kinetic or potential?
Be lower potential.
Potential. Because bonds have stored energy. Yes? Bonds have stored energy. However, the closer they get to each other, so I have two different things getting closer to each other, two individual things. There comes a point when the two nuclei, right, are going to start to do what? Nuclei both have what charge?
Repel.
Positive charge. If the nuclei come too close to each other, what are they going to start to do? Repel. They're going to start to repel each other. And then your potential energy would be raised, which is not what you want. The potential energy is going to be raised. A happy medium. Okay? Anybody know what a happy medium is called?
Ability.
Yeah, a bond. A bond is formed at a distance where the force of attraction and repulsion result in the lowest, or as Aubrey said, most stable potential energy.
Sounds like cool.
Can you figure
It
out
is
like,
Coulomb's
how
law.
far away like the bonds are? And
Stay with me. Stay with
I
me.
keep on asking questions.
That distance, Aubrey, is called the bond length. So the potential energy at that point is called my bond strength. So there's bond length and there's bond strength. And here's how I remember this. The shorter the length, the stronger the strength. That's a Heller original right there. The shorter the length, the stronger the strength. The shorter those bonds are, the stronger the bonds are. So, if I was going to be, if you actually made these molecules, this is actually the longest bond, and this is actually the shortest bond. Actually, the shortest bond. So this is
Bond strength is dependent on the length.
correct. The shorter the length, the stronger the strength.
Good punchline.
Yes. The shorter the length, the stronger the strength. So Aubrey, here's your picture. Here's your picture. Flip your book to page number 302. So here is actually calculating what this would be. So on page 302, I have two hydrogen atoms kind of far apart on the right. Do you see that? Then they get a little closer together, and their potential energy is a little bit below 0. Yes? Then they dip down big time. Why below 0? Because we're starting to store energy, right? We're going to store that energy in the bond when the bond is formed. Then boom, negative 458 kilojoules per mole at a bond length of 0.074 nanometers, a hydrogen bond is formed.
So that's when it's that's like the ideal.
Yes, that's the ideal distance between nuclei for a hydrogen bond. And then if I would continue to push those even closer, then my potential energy goes up. Why? Because now my nuclei are actually repelling. So that is what happens when a bond is formed. And we're going to actually eventually be calculating bond energies.
can you like a way to like release energy? Like, could you like push like the atoms together and to like the point where they like split apart or something like
You can't make that, but that's essentially what a magnet is, right? If they get too close together, it will repel away. Just Coulomb's law. Just Coulomb's law. So, since the forces, so down here, this is this chart that was in the book. Since the forces of attraction, also known as Coulomb's law, I told you it was going to be important. Coulomb's law, that stabilize the atoms when they bond are attractions between electrons and nuclei. The more electrons involved, the stronger the attraction, right? So triple bonds have 6 electrons, so those are stronger than double bonds, because double bonds only have 4 electrons.
Just like essentially thinking about it as like Q1 and Q2.
Yes, you got it. It's the amount of charge related to Coulomb's law. Also, shorter the length, stronger the strength.
Shorter, less distance.
Yes,
You have a higher Q value.
you got it. Good? Flip it. Flip it. That's covalent bonds. That's covalent bonds. So, and then did you guys see a little picture over here on A on page 302? That kind of shows you what the electrons would do, how they start to interact around the positive, but that's not super important. The chart's the important one. Ionic bonds. Ionic bonds. Once electrons are transferred, we were just kind of talking about this on the test. The electron cloud looks like this. Cation did what with an electron? Lost. Anion did what with an electron? Gained. So the electron cloud on an anion is going to be larger because there's more repulsion, right? The electron cloud on a cation, you lost a whole level of shielding, right? Because metals aren't going to bond unless they're losing that outer shell. See? See. Don't flip the page to 305 yet. Okay? How does an MRI, don't do it yet. How does an MRI work? This is really cool. So an MRI is a magnetic resonance image. What is your body mostly made of? Water. And a water is a what type of molecule? Polar. You have the 2 hydrogens on one end and the oxygen on the other end, yes? So you have positive one side, negative on the other. So if you put magnets on both sides of you, you could line up all the water molecules in your body all going the same way for a second.
That's so weird.
Really stinking cool though. Really stinking cool. Then you turn that magnet off and then those water molecules go back into their regular positions around like an organ and you see the picture.
Oh.
That's how an MRI works.
Is that why you can't put like metal up? That's why you gotta like take off like metallic.
Yes, because the magnet is so strong. This is super sad but true. Somebody was doing an MRI in a room, and there was there was somehow a tank of oxygen in there. Well, oxygen tanks are magnetic, and the person that went in the little tube died because it just sucked that tank right in there and just killed him.
Nuclear loss.
So, anyways, don't wear metal in a magnetic MRI, and you won't. This was like way like back in the 50s.
Oh, okay.
So like that wouldn't happen now. But now flip it to page 305. So this shows you how it works. You're just aligning your water molecules, and that's not water. I think that's like hydrogen fluoride. I don't know what they're talking about here. But it works the same for water. That's really cool,
It's cool, but it's also.
right? You can't feel it. Yeah. You can't feel it. It's just a magnet. But if you understand how science works, you understand how the world works. That's how an MRI works because water is a polar molecule. Kind of cool. So, the strongest ionic bonds form between ions that are big or small. What would you say? Which one will have the strongest bonds? Why? Coulomb's law. Right? Coulomb's law, we want a low denominator, yes? To get a low denominator, I need a short distance. True ionic bonds come from high differences in electronegativity. Electronegativity. I've written that too much today. So what is going to be a true ionic bond? Francium and what? Fluorine. That's really just your true ionic bond. What would happen? Well, francium is radioactive, right? And fluorine is a poisonous gas.
Would we make a bomb?
Has francium chloride ever actually been
Brady,
created?
what the heck?
I don't know, in all honesty. I'm not sure. I'd have to Google that. Look that up tonight.
Find out.
So here we go.
There's like 1 gram of fluoride.
Here's what I could ask you. So we're going to start applying Coulomb's law now. So last chapter, there was no application. This is the application. Which one, sodium chloride or sodium bromide, has the stronger ionic bond? Sodium chloride or sodium bromide? Circle the right answer.
gonna be,
Is it
Oh, it's-
NaCl? Because bromine, so.
We're doing this one. We're doing the words here.
Sodium bromide.
oh, okay.
Sodium chloride or sodium bromide?
Oh, sodium chloride.
Sodium
It's sodium chloride. Why?
Chlorine is smaller than bromine.
Chlorine's smaller than bromine. And you would also agree, what's the charge on sodium? +1. What's the charge on chlorine?
-1.
Is there a difference in charge? What's the charge on sodium? +1. Charge on bromine is. So if the charges are the same, then you have to compare their sizes.
If the charges are different.
So if the charges are different, that means the size will be the same. I'm never going to make you do both.
Thank you.
So do these. Which one has a stronger ionic bond in each one of those sets?
Okay, outside of the size, what did you say was another factor for the?
Distance.
I think it's NAF because that's greater distance.
First one. NAF or KCl, what'd you say? Yes, I agree. Why?
Greater.
So NAF, right? Na and K. First of all, these all have +1, -1. Yes? Why NAF versus KCl? Well, Na is smaller than K, right? And F is also smaller than Cl. What about over here? +1, -1, +2, -2. MgL. Higher charge, right?
They would be for
Higher charge. The charge wins.
the charge though.
The charge wins.
In terms of size, which one would be bigger? Just because like I'm looking at the periodic table and sodium.
It doesn't matter. It doesn't matter. If the charges are higher, the charges win.
I think it's bigger than Mg.
This is what you'd have to do on the test. So look at the charges, right?
You go to charge first. And
Charge first, then size. Charge, then size. So the ions in ionic solids are held in a 3D structure called a lattice.
This thing.
A lattice structure. So this is what makes them brittle. So here is sodium chloride. Lattice structure. Why is this brittle? Well, first of all, which one's sodium?
That's the big ones.
No,
Oh, sodium.
the blue ones, right? Because sodium lost, chlorine gained, yes? Why is this brittle? Well, watch this. You can break off, right? You can break off a whole piece of this very easily. Positives align with the negatives, negatives align with the positives. So this is a lattice structure. So here's one ion, here's another ion. Don't lose my ions. Don't lose my ions. There's one missing somewhere here. There's one missing here. But you guys can pass that around. It's just kind of fun to play with. Anyone know who Will Gasteyer is? He was a student. He was like 8 or 9 years ago. Will Gasteyer? No, okay. He lost one of those, I think. I still blame it on him. Or Alizar Coetzee, one of those. Oh my gosh. Beep. All right. So this results in them being brittle, and you can kind of see why they're brittle. It's held together by strong electrostatic interactions. The strong bonds give ionic solids high melting points and boiling points and low vapor pressures. Electrostatic, just like electric forces. More on vaping, next next chapter. So, we don't know what vapor pressure is yet, but you will next chapter. We'll get to that next chapter. So, valence
Maggie.
electrons in a metallic salad, did I say salad? Solid, are considered, I was thinking about Chemsgiving, delocalized. Yeah, there's no solid at Chemsgiving. Put a star around delocalized. Delocalized means they can flow across. These electrons can move. That's why metals can conduct electricity, because of delocalized electrons. The other thing about ionic solids, they have high melting points, high boiling points. Also, when you dissolve them in water, they can also conduct electricity. All right? So you can conduct electricity in an ionic solid that's been dissolved in water. Because think about it, you're going to have your positive and negative ions floating. It can flow. So this sea of electrons that flow over positive metal ions, the best example of this is alloys. So an alloy, and there's two types of alloys. One is an interstitial alloy. So this is forms of different radii, essentially. And a substitutional alloy forms from atoms of similar radii. And you might be like, Heller, what the heck would that look like? Flip the page.
I can't even
Flip the page. Flip the page. So this page is what these look like. Here's a substitutional alloy, same size, interstitial alloy, different size. What would you have to know about that? You'd probably be able to identify that as a picture, right? Or you could be given two different atoms, figure out their sizes, and figure out if it's substitutional or interstitial. So, why could an ionic solid conduct electricity? Well, or when, I already gave this away. If you dissolve it or make it molten. All right, dissolve or make it molten, or melt it, essentially. So dissolve or melt it. What would that look like? Well, here is a lattice being attacked by water ions. This looks kind of like out of this world, right? But you got a positive side, negative side, and it just rips them off. So the hydrated ion, right? You have the positive side of the water on that. The hydrated cation has the negative side of the water on it.
Wait, but those hydrogen atoms are like, they're positive, so why are they like so close?
That's why they're against the negative. Why are the hydrogen atoms close to each other? Stay tuned. Stay tuned. Ionic solids are polar for the most part. So, the polar water molecules are attracted to the oppositely charged ions. Flip the book to page 308. All right, page 308, you can see that water is a polar molecule. It definitely has a positive and a negative side. So the idea of like dissolves like, right? This is the idea of like dissolves like. If you have a polar molecule and a polar molecule, it's going to dissolve. Water's polar, salt is polar. They dissolve. Why? The positive end of salt reacts with the negative end of water. That's why they can dissolve in each other. That's what the like dissolve likes mean. But oil, which is all nonpolar, all even charge, right? Doesn't dissolve in water because there's no interaction between those. That's what like dissolves like is. And that process is called hydration when you dissolve something in water, because the ions are now said to be hydrated. So the ions are free to move, so it's a great conductor of electricity. If a non-polar solvent was used, nothing would be attracted to the ions due to no dipole moment. There's no uneven distribution of charge. So the ionic bonds would stay solid and not dissolve. And yes, I know that those were run-on sentences. Flip the page. We're going to finish this. We're going to finish this. Can I flip mine?
Yeah.
Okay. The hydration process increases the entropy, which we're not going to say more about entropy now, except for just disorder. All right, we will later, of the system. That makes sense, right? You have that lattice structure into ions everywhere.
Okay.
More disorder. In simplest terms, you could think of compounds being 100% ionic or 100% covalent, which is what you've learned to this point. But these only occur at the extreme ends of a sliding scale. So, the actual types of most bonds are intermediates between the two, with a largely covalent substance having some ionic behavior or vice versa. Which means the majority of group of compounds are what? Polar covalent. Boom.
Clap it up.
Polar covalent. That is most of chapter 8.
Well, there's still chapter 9.
Well, that's not all of chapter 8. So I will do the rest of chapter 8 on video notes for the Monday after, because we won't be here.
Right now, it's out of sight, out of mind.
And then chapter 9 is where we get into, that's actually not even all of chapter 8, because chapter 8 is also Vesper. Chapter 9 is hybridization, all that stuff.
What's hybridization?
You'll see. Just promoting some electrons, it's fine. It's fine.
I don't trust that.
I'll show you the long way, but then I'll